All right, very good. Well, thanks to Greg and everyone who's attending here for giving me a place to tell you about quantum information and a platform for this talk. Let me first start, as I did with my gauge theory talk, with a little bit of prologue and a little bit of motivation. So why quantum information? Why is this an interesting thing to study? So as usual, if I'm going to ask you to sit through a very long talk, I should motivate it first. So I'll do the same thing I did before and motivate this topic from a few different directions. So one from sort of the historically first place that this subject was of interest, which is in kind of traditional physics, then a more modern perspective from quantum computing, which I'm using loosely, this term quantum computing, both to refer to computing itself and to quantum communication. And then from my field, something from high energy theory, to tell you that this is very interesting and a novel subject. And then at the end, there'll be one little bonus single slide vignette about what Greg and I have been thinking about in this area. Okay, so what's the first vignette? This is something called the EPR paradox. So if you haven't heard about it, let me set up why this is interesting. For those that attended my gauge theory talk, I motivated part of that talk by saying that we have a principle in physics called locality. So what is locality? Locality is the statement that we expect that in physics, the effects on some localized object, some body, like a positron, for instance, if you have a little positively charged particle over here, say on Earth, you expect that the behavior of that localized object can be affected by nearby things. So for instance, maybe another positron that's very close to it on Earth, but you expect that it is not affected by conditions very far from the object. So if there's an electron on Mars, you expect that the system should somehow be decoupled. By locality, the thing on Earth should not care about the thing on Mars, or if it does, it should take a while for the information to propagate. So this is something we like, and part of what makes entanglement interesting is that it appears to violate this principle of locality, and it appears to very badly violate it. So this seems to be an exception to this principle of locality. So the sharpest way to see this apparent violation is in a thought experiment, which was proposed by Einstein, Podolsky, and Rosen, and it's named after their initials, EPR, and it's called the EPR paradox. I'll argue it's not actually a paradox. It's a feature, not a bug. It's something true about the world, but it was originally presented as a paradox. So let's see what that paradox is, that supposed paradox. I'll set up a little cartoon for you. So don't worry if you don't know what a pion or any of these terms are. All that really matters is that the setup is we imagine that there's some particle sitting here. It's some particle that has no spin. If you don't know what spin is, that really doesn't matter either. Spin, just think of as some vector that has to be conserved. So if this thing starts with zero spin, the zero vector for its spin, then subsequently the total spin of the system must also be zero. It's some conserved quantity. So this spin zero object decays. The pion splits into two daughter particles. So there's an electron and a positron. Each of those have some spin 1/2. So for instance, maybe this guy could be spin up and this guy could be spin down, or vice versa. But since angular momentum is conserved, you can't have two spin-up particles, because then you would have gone from a zero spin or a zero angular momentum configuration to one with non-zero angular momentum. So that's all that happens. Some spin zero particle decays, and the two decay products rush off in opposite directions. So here's the apparent paradox. If I'm sitting over here, so here's CF on the right side, if I'm sitting at this right detector, which could be very far separated from the left detector, could be light years away in principle. If I'm sitting here and this decay product, the electron, arrives at my detector and I measure its spin, and I get spin up, then I instantaneously know that the electron that arrived at the other detector very far away in principle is spin down by conservation, since you must have one of each. So this is the usual framing of the paradox. It seems that information about something that's very, very far away has been instantaneously transmitted to me, since I could be in principle light years away from the left detector, but I know that the electron arriving at the left detector is spin down. Okay, I've intentionally presented this in a way that if you're thinking carefully about this, you should say, this is totally uninteresting. When I first heard this presentation, I found this boring. I originally thought there's nothing remarkable about this at all. So I'd like to very carefully explain why there is actually something remarkable about this, and it's not as boring as it might seem. So to do that, let me sharpen the reason why I, and perhaps you, thought that this is boring. So let me describe a totally different experiment that may look superficially similar. This is a non-quantum version of this experiment. So in this experiment, there's a lab assistant, which could be K-star, for instance, who's sitting in this middle location, and there's two closed boxes, and K-star has two socks. There's a red sock and a blue sock. Now again, I'm over here at this right detector, which could be very far away, and I can't see what K-star is doing, but he's been instructed to flip a coin and randomly choose one of the socks to put in the left box and the other sock in the right box. So I don't see what he does, but K-star flips a coin. Maybe he decides to take the red sock and put it in this box, and take the blue sock and put it in the other box. So K-star does this and then puts the boxes on conveyor belts that take them very far away to the two detectors. Now, when the box arrives at my detector and I open the box, I see there's a red sock inside. Now, I could say all of the words I said on the previous slide. Oh my, information has instantaneously been transmitted to me. I know immediately that someone who's sitting at the other detector will find a blue sock. Is this not a violation of locality? This seems very strange. But of course, there's nothing strange about this at all. It's just that something happened and moved very far away. And because I knew the data generating procedure for how the two socks were assigned to boxes, I can make an inference. So this is not why the EPR paradox is a supposed paradox. This is totally boring. So if I'm going to argue to you that the EPR paradox is interesting, I need to explain why this is different from the EPR experiment. So why is this different? Well, the reason has to do with a somewhat subtle fact called these Bell inequalities, which I will not prove for you, but I'll just sketch the flavor of the argument. So it's possible to prove, under very general assumptions, that any experiment wherein you have some data generating procedure at the location of the particle decay, so some way of randomly assigning an upspin to one of the particles and a downspin to the other particle, via any random process whatsoever, being totally general. You can prove that any such data generating procedure that assigns spins and then sends the spins off in the other directions, similar to the sock experiment, would have outcomes, probabilities for our measurements on the two sides that obey certain inequalities. So here's one of them. Here the spins are represented as vectors, so one inequality you can prove is that the difference of the probabilities of measuring this vector SL for the left spin and the vector SR for the right spin, minus the probability of measuring the spin SL for the left spin and some other reference vector, so fix some vector S0 for the right spin. The difference in absolute value of those probabilities is bounded. It's bounded by 1 plus something. Okay. So that's fine. I'm not going to prove that or really go into any detail whatsoever, but the takeaway is that there is some universal set of bounds that such experiments must satisfy. Here's the surprising fact. The predictions of quantum mechanics in the EPR experiment, the one where the pion decays, violates these inequalities. There's a violation of the Bell inequalities. And this prediction is borne out in experiment. You can do experiments where you measure the spins on the two sides. These experiments have been performed with the two detectors separated by tens of meters, fairly far, and the violations predicted by quantum mechanics are seen. So how can we interpret these violations? I mean, the only possible out, as far as I'm concerned, some people cook up very strange cranky theories to have other outs, but from my perspective, the only sensible way to evade these inequalities is to say, it was not the case that in the EPR experiment, there was some random assignment of an upspin to one of these and a downspin to the other via some random process. And then throughout the entire trajectory of these electrons, they maintained those spins that were assigned to them at the beginning. So I'll say it again. It is not true in the quantum version of the EPR experiment that the two spins had somehow decided which was up and which was down at the time of the decay, and they stuck with that decision throughout the entire time of flight. That cannot be true. So that's why this is surprising. What is true then? Well, the current understanding is that It was not the case that one spin was up and one spin was down all along. They did not have independent spins before reaching the detectors, but as we'll explain eventually, they were in an entangled state. So I'll explain this notation over this talk and hopefully the next one, but this is a representation of the spins of the two states, and a feature of the state I've written here is that we cannot speak about individual properties of each particle in this state. You can't say one spin is up and one spin is down. You may only speak about properties of the combined system of both spins. That's it. That evades these general inequalities, which assumed that each spin had a well-defined value, up or down, or more generally some vector, at all times throughout the time of flight. This is the evasion. Okay. So now why is the EPR paradox considered a paradox? Well, another thing quantum mechanics tells us is that when we perform a measurement, this entangled state here at the top collapses. So it begins in an entangled state, then I measure one of the spins at one of the detectors, say the right detector, and then the state collapses. That collapse is a physical effect. So after measuring one of the states at the right detector, the other detector or the other electron, say near the left detector, collapses as well. So it's not like the sock example. In the sock example, when I find the red sock, nothing has changed about the blue sock. I just know that it's blue because there was one of each. In this quantum version, when I measure the right spin, something does change about the left spin. It's not merely one was up and one was down, and I figured out which was which. It's that the left spin was in an entangled state, and when I measure the right spin, it instantaneously collapses. So my action of performing a measurement on the right spin instantaneously affects the state of the other spin, even if it's very, very far away. That's what's spooky about this. That's the violation of locality. The collapse of the state is instantaneously transmitted from one particle to another, regardless of physical distance. This has been observed in the lab. This has been done in cases where you can perform precise timing measurements down to the nanosecond. Light travels at about 1 foot per nanosecond, and it has been conclusively shown that this wave function collapse happens faster than what could be communicated by a speed of light delay between the two detectors. So this is a genuine effect. When I collapse one of them, the other collapses, and no signal passes between them. It just happens instantaneously. That's very spooky. Okay, so hopefully I've given you a flavor for why entanglement is seen as a strange phenomenon, that something seems to violate locality. Okay, let's do the second one. This is a very different perspective, more of an engineering or computing perspective, or really quantum communication, which I think of as a subset of quantum computing. So let's motivate this. That previous discussion about the EPR experiment seems like this entanglement thing that I'm talking about is just some quirk. It's some strange feature of these probability distributions. In particular, they violate some inequalities. And maybe you think that's a mere curiosity. Okay, probabilities don't behave the way that I thought in quantum mechanics. But people in quantum computing don't take that perspective. They view entanglement not as a quirk, but as a resource, a concrete resource, just like energy. You can use energy to do something like heat up your tea or charge your computer. And people in quantum computing view entanglement as a resource totally analogous to energy. So let me explain why they do that, why they view that as a resource. So let's think of another setup. Suppose that Greg is taking a vacation and he's going to holiday on Titan, which is one of Saturn's moons. So he goes off to Titan. I stay on Earth. And suppose that by whatever mechanism you like, Greg and I each have one of the two particles in one of these entangled pairs, just like the two electrons in the electron and positron in the previous example that came from a pion decay. So it doesn't matter how we got the two. If you like, you can think of this as, oh, there was a pion between us, it decayed, Greg held onto the electron and I held onto the positron, and we carefully kept them entangled and avoided measuring them. Or if you like, you could think, well, before Greg left for holiday, we were on Earth and we constructed an entangled pair of, say, two electrons. And I held onto one and I gave the other to Greg, and he took that on his trip to Titan. Doesn't matter. View either of those procedures if you like. But just suppose that we've done that. Now I'll show you something interesting we can do if we're in this situation. This is called quantum teleportation. So what is the problem that quantum teleportation lets us solve? So the problem is now I have a friend who's on Earth with me. I have a friend who has a second electron. It's a different electron from the ones in our EPR pair. And I would like to transmit the state of that electron to Greg. So if Greg is in his lab on Titan, I would like to allow Greg to have an electron in his lab which is in the exact same state as the electron that my friend has. So it's some very interesting state, and I'd like Greg to have it so he can do experiments on it, for instance. How might I do that? Well, the first few ideas that might come to mind will fail. So as we'll see, you might first think, well, okay, just measure the electron very carefully, write down a set of numbers that tell you the state that it's in, and then send a radio signal to Greg so he has those numbers. I can't do that, because if I measure the state of the electron, I measure one property of it, that collapses the state. So I can't do a sequence of measurements to get all of the numbers I need to specify the state and then send those to Greg. It just doesn't work. That's not how quantum mechanics works. Okay, so your next idea might be, well, okay, this electron is kind of like a bit in a computer, and I can copy files on a computer. So why don't you just make a copy of the quantum state? If you have a copy, there's lots of things you could do. I mean, the easiest thing to do is you could just send the copy to Greg and then he has it. But let's assume you can't do that. Let's assume it's hard to send something to Titan. So maybe another thing you might think is just copy the state a bunch of times and then perform different measurements on each of the copies so that you now have the list of numbers you need, and you send that information to Greg via radio signal. I can't do that. There's a theorem in quantum information called the no-cloning theorem. You cannot make a copy of a quantum state and preserve the original. It's just impossible. I can't prove it rigorously for you right now. It would take too long, but if you want, you can ask me when we stop for questions, and I can give a very intuitive physical proof of this result. Okay, what if you say, okay, fine, don't do that, but just think of some way of encoding the state of the electron, being totally agnostic as to how you do it. Some way of encoding the state of the electron in numbers, and then send those numbers to Greg by the radio signal. I can't even do that, even though that procedure was very general. There's a second theorem. A quantum state can't be transferred by solely classical communication, or by classical communication I mean sending bits via radio signal, the sort of thing we do via Discord. I type something and that gets encoded in bits that goes to you through the internet. You cannot communicate the full state of a quantum system by only classical communication. Okay, well now it seems like we're screwed. Is there any way to do this? You might ask, is there any way at all for Greg to recreate the state of my electron in his lab without me sending it to him? And the ingredients we're allowed to use to do that are just sending the radio signals I've been discussing and using this shared EPR pair that we had the foresight to construct before he left. But that's it. Okay. The answer is yes. There is a way to solve this problem. I won't explain it in detail, but I'll just give you sort of a slogan-level explanation of what we do. So what I do on Earth is I take the friend's electron, the one I want to transmit, and I bring it together with my half of the EPR pair. So I take the friend's electron, so this is the friend's electron, and I bring it close together to my electron that's in our EPR pair. And that joint system of the two electrons is something I can now perform measurements on. So I do a particular joint measurement, which I can explain to you if you like, but it's measuring some combined spin of the system. You can think of this as firing the two electrons through maybe some magnetic field that will deflect them in one way or the other, depending on their spin. And I get one of 4 results. There's only 4 possibilities for the combined state of this system. I get 1, 2, 3, or 4. The explicit formulas don't really matter. There's just 4 results. Okay, so I do the measurement. I get one of those 4 results. Now I send the result of the measurement to Greg. I only need 2 bits of data to send a number which can be between 1 and 4 inclusive, right? There's 4 possibilities. A bit is 0 or 1. So if I have 2 bits, I encode the first possibility as 0, 0, the second possibility is 0, 1, and so on. This is 1, 0, this is 1, 1. 2 bits of data, that's it. I send the 2 bits of data to Greg via radio. Now, we've agreed ahead of time that when he gets that signal, he performs a particular rotation on his other half of the EPR pair, his entangled particle, and these are the 4 that he does. If he gets the 1 or the 0, 0, he does nothing, and in the other cases, he just performs a rotation of his half of the EPR pair around some axis that we've agreed upon. Here's the magic. After doing this procedure, provably, Greg's electron will be in the precise state that my friend's electron was in before the procedure. This is why it's called teleportation. I've somehow teleported my friend's electron exactly into an electron in Greg's lab. It's an exact reproduction of the state of the friend's electron before this process. Now, you might be thinking, well, it sounds like what you've really done is just performed a certain comparison between the friend's electron and the particle in the EPR pair, right? Maybe by performing this joint measurement, you've just compared the two and then sent the comparison between those two electrons to Greg. Is that what happened? And the answer is no. If Greg's electron was in a particular state, and my half of the EPR pair was in exactly the same state, but they were not entangled, and you repeated this procedure, it would fail. So this procedure only works because our particles were entangled. Okay, so the entanglement is critical. Finally, you might say, does this violate the no cloning theorem? Because now Greg's electron is in the state of the friend's electron. Well, no, it doesn't violate the no cloning theorem, because after this, the friend's electron is, well, we say it's destroyed, but of course the electron still exists. We haven't destroyed the particle, but the information is destroyed. The friend's electron is scrambled into some random state, so we have not cloned the state of the electron. Okay, that should seem very magical. So just to summarize what we've done, we've transmitted the full state of a quantum system, which again, you cannot do with purely classical communication. So people sometimes say that the amount of information we've sent is LF0 bits, because no finite number of bits can ever communicate the full state of a quantum system. So this is like infinitely many bits. We've done this by using one entangled pair and sending 2 bits of information. And since the pair is used up by this process, this is the sense in which I mean entanglement is a resource. We have spent a unit of entanglement, one EPR pair, and used that to perform this process of sending the state to Greg. So that's why entanglement is a resource. You can do lots of remarkable things with this quantum computation type stuff, but you have to use entanglement typically to do it. So here's a nice picture just to see what we've done. Time goes vertically. Each of these lines is a world line of some person. So here's me, here's the Ferk world line, here's Greg, he's over on, say, Titan. And what's happened is we started with some spin 0. We used that to make an EPR pair, so that's the dotted line. My half is this half of the dotted line over here, Greg's half is this one over here. Then at some point, maybe 5 years later after Greg goes to Titan, I decide, hey, my friend, who's this world line, has some electron which is in some particular state, represented by this arrow. He brings that state close to me. And then this box is performing the joint measurement. I perform the joint measurement and send it to Greg. He receives that process, or that result of that measurement, and then does what we described. And now he has this electron that is in the state of my friend's electron from before. So this should seem extremely spooky. How did the information about the electron get from me to Greg? It could not have gone purely through the classical signal, because 2 bits is not enough information to communicate the state of an electron. So in a certain very precise sense, the path, if you like, the way that that information was sent to Greg went backwards in time, right? If you imagine Greg starting here and going backwards in time along the dotted line of his half of the EPR pair, then going back to here, and then coming back forwards in time, and then crossing over here to go down to the electron. In a certain precise sense, this quantum teleportation has allowed us to reach backwards in time to grab the state of the electron and bring it up to where Greg is on Titan. That's spooky. That's extremely interesting and mysterious, that we're allowed to do something like that in a way that's consistent with the rest of physics. Right? This is not real time travel. We haven't sent a signal back in time, but in a limited sense, we were allowed to use a resource by going back in time through this entangled world line. So here's a quote that I like that explains this. This is from the textbook by Nielsen and Chuang. It reads, "So at this stage, entanglement may appear to be such an abstract notion that the need to quantify it does not seem to be urgent. But then, once upon a time, energy must have seemed a very abstract notion indeed, and now there are thriving industries whose role is to deliver it in precisely quantified amounts. So perhaps our governments will eventually have special departments of entanglement to deal with these things." Okay, last major vignette, and then we'll move on to the real part of the talk. This is the Ryu-Takayanagi formula. So if you know me at all, you might be asking, okay, why are you interested in this? Because my research interests focus on strings, fields, and gravity, and this seems to not be directly related to those. So the answer is that the reason I'm interested in this is because of holography. So something we've learned from string theory in the past 30 years or so is that there's a remarkable correspondence between theories of quantum gravity, which are theories that live on some manifold, in this case a negatively curved spacetime manifold, and other theories called conformal field theories that live on the boundary, or more precisely the conformal boundary of such a spacetime manifold. So this is believed to be an exact equivalence. This is something that's argued for and to some degree proved in string theory, depending on your standards of what constitutes proof. So this is something we know. Now, let me tell you about one aspect of this correspondence. Let's go to the boundary, which is again some manifold, fix a subregion A, which might look like this region A on the side of the picture, which I'll zoom in on in a moment. And again, I'll explain this notation a little more later, but in some given state of this field theory on the boundary, you can have entanglement. You can have entanglement between degrees of freedom in the region A and its complement. And we have a number. There's something called the von Neumann entropy, which quantifies the degree of entanglement between those two regions. And again, we'll see what this partial trace means eventually, but this is some number you get that measures how entangled the region A is with A complement. Now, I just told you there's an exact correspondence between this theory on the boundary and a gravity theory in the bulk. So if you believe that, you should ask, can you find something in the gravity theory which corresponds to this quantity in the boundary? If there's an exact correspondence, this number that I compute in the boundary theory should correspond to something in the bulk. And since gravity is a theory of geometry, you might think, well, is there a geometrical object which encodes this entanglement entropy? And the answer is, again, yes. And it's beautiful. So this entropy, the von Neumann entropy, is exactly given by the area of some surface, some extremal surface, which is here called gamma sub A. And that surface has some properties. It has to be homologous to the region A, which means I can't have like a black hole in here, which would be like excising a point. Then I wouldn't have, this surface would no longer be homologous to A if I've excised a point by putting a black hole in, for instance. But up to that, gamma A is just a surface who is homologous to A, with the boundary being the same as the boundary of A, and which satisfies some extremality condition. So it's some geometrical surface that has geometrical properties like area. And the area of this surface measures the von Neumann entropy or the entanglement. So this is very nice. This is a correspondence between an information theoretic quantity in the field theory and a purely geometrical quantity in the bulk, namely the area of some surface. So this is why string theorists have become interested in this subject recently. Okay, so that's it for the major vignettes. I'll have one additional slide of motivation before moving on, and this relates to what Greg and I have been thinking about, which is a project involving homological algebra. So from these vignettes, you may be getting the impression that entanglement is, in some sense, an obstruction, right? I told you in the EPR part, the vignette, that you cannot explain the total state of an entangled system by assigning spins to each of the subsystems, right? I can't say one spin is up and one spin is down. So in a particular sense, entanglement is an obstruction to describing a global system using local descriptions. Now that sounds a lot like cohomology, right? So for instance, in de Rham cohomology, by the Poincare lemma on a very small open set, every closed form is locally exact, but generically you cannot describe a closed form as globally exact, and the obstruction to doing that is measured by cohomology. So that sounds a lot like entanglement. And indeed, this can be made precise. So as Greg and I have seen, there's a cochain complex, which looks like this, and the only interesting cohomology you find for this thing is kind of the middle cohomology, if you like. So it's the kernel of this guy modded out by the image of this guy, in the same sense as we usually look at closed forms mod exact forms. And a bipartite system is entangled if and only if this cohomology is non-trivial. So there's a cohomological interpretation of entanglement, which is something we're thinking about. Okay, this has been a long introduction. Back to the prologue. So I'd like to emphasize one more time that this is a very interdisciplinary and active field. There's a lot of money being thrown at this area right now. I think historically the only close analog of how much money is being thrown at quantum information right now is the space race between the US and the Soviet Union, although in this case the main rivalry seems to be quantum information in the US and quantum information in China. So a lot of funding goes to people in various areas working on this field. This is one such collaboration, which is where my postdoctoral advisors here get funding. One of the places they get funding from is this IT from Qubit collaboration. So it's an exciting field. And the goal of this talk, or this series of talks, is to start to develop some of the language and notation that people use when working on this area. So my hope is to give you some of the background and the context to read papers in this area. So it'll be a bit of a slog. There's a lot of textbook material that, if you haven't seen before, I have to work through, but I think the payoff will be worthwhile. Okay, so already half an hour or a little more in, but that was just the prologue. So to summarize, we've seen 4 ways to think of entanglement: as these strange correlations that violate Bell inequalities, as a resource for doing interesting things, as an area in a bulk spacetime, and as cohomology. So I will now stop attempting to motivate the subject, because if I have not yet persuaded you that this is interesting, then you have no soul. So the plan for the rest of the talk, now that we finished the prologue, is the following. First is some somewhat standard material on Hilbert space. The goal of that is to fix notation. If you've studied Hilbert space as a mathematician, I want to show you how we speak about it in physics notation and map maybe what you know onto a new way of writing it. Then a little bit on observables in Hilbert space, and then a physical toy example to help build up some intuition. And then at the end, I'll explain what I have not told you yet, and if we continue this series of talks, what I'll discuss next time. Okay, so I should pause here. I'm going to stop the recording and then restart, but are there any questions